Hi everyone. We are about to start our webinar now. So this webinar is with Devrup Banerjee. He's just pursued his PGDM from Great Lakes, and he's also a MachineHack Grandmaster. So the agenda for today's webinar is going to be how to crack the data science hackathon. He'll be primarily discussing about the best practices to follow while participating in a data science hackathon, also on his approach to a problem statement. So he'll be taking us to one of the problem statements. He'll be presenting it end to end. He'll also be talking about the best resources and let's say the knowledge base which he has used to learn throughout his journey and how he has been doing it consistently since I think for a year and a half or two, and how to pick up a right platform as well to compete. And in the end of the webinar, we'll have the Q&As exclusive to all the questions, which will be answered in the end of the webinar. So I'll be just handing it over to Devru so that he can just quickly get started.
Thank you, Anurag.
Over to you, Devru.
Yeah. So good morning, everybody. Devrup this side. So today we will be explaining approaching a ML hackathon, but along with it, I'll also try to share all my experiences that I have found gave me good results in normal general hackathons, other than the particular one that we will be discussing today as well. A bit about me. So I completed my PGDM majors in analytics from Great Lakes. I was given a job in Hexaware as a data scientist. I'll be joining it soon because of COVID. The joining got delayed, and so the MachineHack platform, as we all are big fan of it, we compete every weekend at it. So it has been a huge motivation for us to keep improving our applied ML skills on this platform. And I personally have learned a whole lot of stuff by just competing in these hackathons and attending their webinars they conduct every time. Like recently, I attended a Vision webinar on Vision webinar 2020 as by Data Science Associations, and it was a whole lot of knowledge that they impart in one session. So yeah, thanks to MachineHack for arranging this thing, Analytics India magazine, of course. Moving on to today's agenda, you will be seeing all the processes that I follow, the step-by-step methods that I take on to approach a hackathon. You will also be seeing my strategies and few of the tricks and secrets, if you may call it, that I use to boost up my scores sometimes. I'll be sharing everything I know in two parts, mainly from a increasing your score perspective and also keeping in mind the real world stuff, which will work in a hackathon but may not be working as well in the real world. So I'll be giving those perspectives as well. So I guess we can start right now. The first thing that many of us do, which every Friday 6 p.m. is download the problem statement. That I don't think we have to explain anymore. So right now, the problem statement we will be talking about is a e-commerce platform price prediction hackathon that happened a couple of, I guess, 1 month back. This was one of my first hackathons which I topped in the MachineHack. The code here, the tricks I used here were initially pretty basic, and I concentrated on feature engineering, more to say, to trump this thing. But later on, I developed few tricks of my own, so I have incorporated them as well in my notebook. So Anurag, I think we can start the session right now, the whole thing, right?
Yes, Devru. We can start now.
Okay. So what this problem statement meant was that they had an e-com platform data for 2 decades. They wanted to know, they wanted to predict the price of a particular item in an e-commerce store, given a few features explaining their variations, the target variations. Their evaluation matrix was RMS LE, root mean square log error, and the two most important things that you have to do when you encounters a problem statement is look at the evaluation metrics, get it by heart, and then reading the overview, get an idea of from where can this data set have come from. Like, is it a transactional level customer data? Which level of data this is? Or did they get it from a population, or did they scrape it from somewhere? Or is this a normal log data? For the data set we will be using right now, this will be e-commerce store data. So all the prices that you see are real life prices now, and it has been taken over a time period there. So there is a temporal dependency here. We have to take care of it, although it's not a time series problem. But we have to keep it in mind that it has been gathered over a time period, certain time period. So I'll be showing you the data and all this. Now, approaching part, there is a fixed module to every ML problem. And I say ML because I haven't used DL till now. I believe I'm not qualified to use DL. I am working on it still. So the ML thing is pretty okay for small data set problems. You may need DL when you are encountering big data, large data sets, and yeah, so ML will be enough for this problem. The first thing is problem statement, like I told you. Then comes data exploration part, playing around with the data, seeing what it is, what are the features there are that are explaining my target. Data pre-processing part comes then, which involves, missing values, dealing with missing values, uh, dealing with any kind of inconsistencies in the data. Like, for example, say a customer has an age of 73, but the data is showing that he bought a car in 1900, say, for example. So this will be inconsistency. On all these things affect the ultimate score, because machine learning is all about pattern recognition. And if an error creeps in the pattern, the machine, for all we know, won't be able to distinguish it, but it will take it into consideration, and ultimately your scores will be garbaged. So you have to check it manually also, if these kind of inconsistencies are there or not. You have to go for outlier treatment sometimes if you believe so. But again, outlier treatment is subject to the business problem. A lot of business problems in real life, I believe what we were taught is that we shouldn't do outlier treatment because we will be losing out on information. If you have absolute reason to believe that the outlier you are considering is an anomaly and won't be occurring anytime soon, then you may go for the treatment. Then comes feature elimination, which are already present. Then comes null hypothesis building. I'll be explaining all this, just blocks. The questions you will be building to feature engineer later. Then comes setting up your validation strategy, which is a very important part in any ML hackathons. And uh, in normal courses, you get to learn the algorithms, you get to learn how to predict, dot predict, and dot predict proba. You get to learn dot fit, everything. But no one really talks about this validation strategy and what it is all about. At least I faced this thing. I had to pick up validation strategies from hackathons. Then comes feature selection, which is, I guess, determines what your final score will be. Most of the people winning the hackathons out there, except from Kaggle, I guess, uh, they base their main strategies around feature selection. Now, hyper tuning is a bit dependent on your computer resources as well. So you may go for hyper tuning, you may not go for hyper tuning. It definitely gives a boost if you do it right. And in the end, it comes to ensemble processing and submission. So I won't be talking about ensembles right now. I'll be talking in it. Now, if we are good to go for the problem statement, I'll be moving on to my collab notebook, which is basically, I always work on collab because it's pretty easy to do, and I haven't started in Kaggle yet. So these are a few of the libraries you have to install in collab. They are not present. And Bpscore, SweetViz, is a new thing. So this I didn't use in this notebook, but it's pretty good for EDA purpose. And bpscore I'll be explaining down. So moving on to the data. Here there was a column called date. Now for date, you have to always parse dates in the right format, or you will be having trouble manipulating them later. Now, if you see here, the explaining features are this: product brand, item category, subcategory, subcategory 2, item rating, and date. And the target, which we will be predicting, is selling price. Let me just connect my kernel once. So when we are dealing with so many categorical features, like all these data types are objects, that means they are categorical. And there is only one numerical feature called item rating. This is the first step where you have to determine which kind of algorithm may work or may not work. If my kernel is right now, I can show you the unique categories in each of these features, and you will see that product brand and products have a huge number of unique categories. Now, what we have been taught so far is that we do pd.get dummies and one-hot encode all of them, but that may not be a valid strategy when we are dealing with so many huge number of categories, because the curse of dimensionality comes into play. And also there's out there view is there that tree-based algorithms do not work well with sparse features, like features that get transformed from normal dense categories into one-hot and after one-hot encoding. So yeah, I believe this is done. So for this reason, we have to sometimes think of other strategies than one-hot encoding to correctly uh, manipulate the categorical features. And this is being done because or else you will be left with not an ideal form of datasets for you know handling in the normal process of tree algorithms. So uh, now this is mounted. So yeah, what I was talking about, the unique number of categories. Now, if you see here, uh, product brand is there. It's a whole lot, and they are all categories. What they represent basically is it's 1,000 actually. So what they represent is for each product brand they have encoded the name, and they have encoded the name and not given us the real name. Now there are 1,000 brands, and inside 1,000 brands there may be a whole lot of products, and there is no way we'll be going to one-hot encode these things. Now, how to approach this first is, as we can see, there is no missing values in this data set. Had there been missing values, the common practice is to mean fill the numericals and mode fill the categoricals. But in some cases, I've seen that if you do not mode fill the categoricals and instead keep it like that, LGBM, of course, LGBM and XGBoost are capable of handling these missing values. But even if you fill them with a completely new category, say, for example, just write new in place of missing values, had there been any, that works well too, because the machine will understand for whenever new comes into play, it's something that will be also present in test, of course, if there is missing values in test, and it can map the pattern accordingly. And for numericals, sometimes minus 999 many people use instead of filling in with mean. So they're just filling a random value which lets the machine know that this is something out of the ordinary and you have to map it accordingly. Do not go by the normal sequence of numbers. Now, if you have to put minus 999 or plus 999 or zeros or ones, that completely depends on the problem statement. Sometimes you may feel that the missing value is actually zero. And if you're absolutely sure, you have to fill it with zeros. So here, this problem statement didn't have any missing value, so I can show you in more depth. But you get the idea. Uh, Points to remember here is that, like I told, if you can make sense of missing values, leave them untreated. And here is no missing value. So moving on to feature elimination. Now, feature elimination I've kept ahead of feature engineering is, for this problem, it's fine. But in many problems, we are dealing with a whole lot of features. And sometimes we have to use automated feature engineering tools. Now, it's not a good idea to put all those features into automated feature engineering and wait for, say, 2-3 hours to build up the features. So if we can somehow eliminate a few of the features initially at the very beginning, which may not compromise on, say, the information that we will be getting from the data frame or the data set, then it's perfectly fine to do it. I've done a lots of time that I've simply plot a normal Pearson correlation matrix. Uh, if I plot it here, it will be absolutely rubbish because there's only one numerical feature. There's no point plotting it here, as you can see. But if there are lots of numerical features and the correlation matrix is showing you a good, very high correlation, say above 0.95, you can go ahead and eliminate them. But just ensure that it's pretty high, because sometimes I've even seen correlated numerical features together increase the score instead of having just one of those. So if it's above minus 0.8, 0.98 or positive 0.98, like that, you can go ahead and eliminate them at the very beginning. Now comes the actual stage of the hackathons, which will decide how you are going to score in the whole problem, the null hypothesis building. In machine learning, this is the most important part. If you're using deep learning, I've seen people just score huge number, a good score based on their models alone. They don't need feature engineering that much. If feature engineering is there, of course it's good. But deep learning is capable of selecting features on their own and getting the mapping the feature on feature interactions on their own and stuff. So if you are comfortable with deep learning, go ahead. But if you are like me, starting out in the journey, and you are only comfortable with ML, then you have to concentrate on this part, that is null hypothesis building. Here is what all the initial questions that you think are important, but your data frame doesn't address right now. You have to write them down here. What this data frame was about was that it had a selling price and it had a date when this selling price was valid. It had an item rating, subcategories 2, 1. You can see what subcategories 2 and 1 are. So subcategories 2, I believe, were explaining the kind of products that were here. Yeah, there's a whole lot of things, whole lot of information in these things, and there's no point one out encoding them because you will be losing information. Like if there is a car bike lightning, I've seen somewhere else that there is a car bike normal, but they both mean the same thing. So unless and until you are using a good maybe NLP model to address these issues, you have to do it manually, and there's no point never one hot encoding these kind of categories. I've seen people do that and they lose out on the information stuff. So the initial ideas that I got from this data set was that the target customers of a product has a significant effect on its selling price. Now, that's like MBA 101 what we are taught generally, that whenever a company is making deciding on a selling price, they're keeping the target customers in mind. And I couldn't see that information in this data set. That it was not present. Now, how to incorporate it? What I did was I manually took each of the subcategories to part and assigned them a target customer. For me, the target customers were women, men, unisex, baby, and kid. These are where my 5 target customers. Sorry. And I pickled them up in a file and later uploaded. So how this helped me was that if my target customers explained even a bit of variations in my selling price, I'll be working with extra information than others who are not engineering this feature. This is how feature engineering works. You incorporate as much extra information as you can inside the dataset along with those which are already presented to you. Uh, a few of the more other null hypothesis that I built was that month of September to December considered as festivities in India has a significant effect on selling price. This might be a very normal thing which can come up to you, you know, your thought process as well, that we know how Flipkart big billion sales and Amazon sales generally happen between September to December, So I believe that maybe these months the prices vary and there are not enough features already present in the data set to count for this change, for this variation in target. So this was also a feature that I engineered. Here you can see that I took month of September to December and simply mapped it to my DF train and DF test. Before that, I uh, extracted the year, day, and month from the date column. And this is what I was saying, that if you do not upload the date in the correct format, you won't be able to do this. So that is the first thing. And I kept on doing this mistake initially when I was beginning. So you have to be wary about this too. Now, after that, the other null hypothesis which I built, I believe, was item category information in aggregated form will better explain variations in target. Now, what I mean by this is that if you see the subcategory 2, it's a whole lot of disintegrated information right here. A Frank Miller wristwatches, RS jewel showpieces, Palito wristwatches, maybe they're meaning the same thing. Now think about it. Palito wristwatches and a Frank Miller wristwatches, they're after all wristwatches. They can't have a price like a car, say, for example. So if you keep all these features like this laying there, it might not be well, it might not info well for your problem, because you're not exactly explaining the variations in the target. Maybe you're explaining more than the variations, and it's not a good thing. So this was a bit of a manual work which I had to do here. I mapped everything, all those unique uh, item subcategory 2 which was present. I mapped them to a fixed category. So for example, home furnishing is home furnishing, but home improvement is also home furnishing. You get the idea. I do not have to explain all this, but socks comes into clothing, sleeve black comes into clothing, lens socks comes into clothing, and like that. So what I'm doing here by using these kind of things is, first I'm countering the curse of dimensionality. Now if I had one hot encoded in the very beginning itself, I'll be gone for the count. But after aggregating them to these kind of special groups, I considerably minimize the dimensional part of mine. and also I gave meaning to this column. Now each one of them will have a unique meaning instead of everything, every different kind of string meaning the same thing. And then I mapped them. So this was the third part of my null hypothesis. And the last part, the brand pricing and slab strategy remains same related to other brands in same category. Now, this was specifically for this problem that I used a target encoding to address this issue. What I meant here was that brand pricing slabs and strategies remain same. An Apple selling an iPhone will always cost a certain average price above, say, for example, a Xiaomi selling a smartphone. Now, this will be true for all the temporary dependencies that my dataset has. Now, if I can group these brands according to their prices and say I give Apple class 1 and Xiaomi class 2, and similarly I maintain this order, lower price brands getting a higher number. This is me incorporating a pattern in the dataset which is not already present. So for this thing right here that I was addressing, I did target encoding. Now, how I did target encoding here was also you have to see the similarities between train and test to before you can do the target encoding. Because if your test set doesn't even closely match your train set, it's completely different on a hyperplane, different hyperplane, then target encoding do not work. So, for example, if you are dealing with Indian Apple and Xiaomi prices and you're given a test set where you have to predict USA prices, suppose it won't work. But what you can see here that it's all Indian prices, and if we consider the top item categories: clothing, jewelry, automotive, footwear, and computers, these categories which have the highest value counts, uh, and then we plot this, you know, we see the distribution of each category year-wise. We will be seeing that in train set as well as in test set, don't go by the colors, go by the labels that are written there because the order is not matching. Uh, the distributions of each category for years will be same. What this means is that when a test set data was picked up for computers, it was on me taken at 2017 year, and the first India quartile range lies between 2020 and 2012. And this is true for all the categories here. And the year distribution, of course, it's the same too for test and train. Now, why I had to check this was I will be doing target encoding next, and I had to check the distribution of train and test, and if it matches. So if it matches, then well and good. I can go ahead with target encoding like I told. Uh, Deciding on an outlier strategy, I didn't use any outlier strategy on this problem. The match of trend test was similar, so I guess outlier treatment wasn't needed. What I have seen is that I'm giving an example. Say for example, a particular price, selling price, is being explained by a numerical variable, say item ratings. Now, item ratings can be 5, 4, 3, anything that we have here. We have a whole range of item ratings here. Uh, just a second. Yeah. So for example, if these are my item ratings in train and these are my item ratings in test. Now I'm explaining when I thought it was a good idea to outlier treatments. You can see it's pretty much similar the unique items. I'm not going into distribution right now, but I've seen that it's similar to. Now suppose this is affecting my target variations in a positive way, like higher item ratings, given other factors are constant, my selling price will be higher. This is a simple statement. But suppose instead of 4.3, 4.7 as the highest item rating in both of them, I had a huge anomaly in say 7. A 7 item rating was present in more dominance in train data than in test data. Now what this is indicating is that the higher value prices may be outlier in the test data because it's not present there. So this is one numerical category. If there are several other numerical categories defining the target in a positive way, and the positive part of the numerical categories are higher in distribution in the train set, you may consider an outlier treatment, because you are getting an idea that the values in the higher side of the target may not be present in the test set. But of course this is subjected to validation, proper validation, and you have to see on the leaderboard if your scores are improving or not, and only then you incorporate it always. This is what my experience told me. So when I see these kind of anomalies, I tend to go for outlier treatment. Now here is the target encoding that I did. I did a simple mean target encoding, and I do not recommend doing this if you're absolutely not sure that the train and test data are from the same same time and absolutely have same distributions, because the target encoding part uh, is better done if you incorporate some noise into it, like smoothing. And I've written a function here which does that, just that. So if target encoding is not done properly, overfitting comes into play. And what overfitting basically means is that your validation strategy will show you great scores. Your leaderboard may or may not show great scores, but when the private leaderboard comes into play, it will all fall apart. But as you can see here, a Apple price, a brand like Apple and a brand like Xiaomi will always have their classes same, regardless of if I'm target encoding wherever train test. That's what I did here. Based on the mean prices of each of those brand category and item category, I gave them a class. So for example, an Apple MacBook is getting a much lesser class than Xiaomi, say Redmi, normal phone. Now, I'm giving a lesser class to the preferable brand. You can give a higher class too, but always maintain the order. If you're giving a higher class to the better selling price, then you have to maintain the order to give a lower class to a lower selling price. I did the reverse. You can do it also. So coming on to this concludes my feature engineering. So if you have any questions regarding this, you can ask me here. I'll be moving on to Bpscore and its importances, and what this means actually in validating what the feature engineered, the features you engineered, how it can validate them. Now, Bpscore, I came across this wonderful Medium article I'll be sharing the link with. It says that whenever a correlation matrix, we plot a correlation matrix, we only see the linear relationship between each feature. This is true. It uses Pearson correlation for plotting those numbers. Now, there may not be a linear correlation between two features, but there may be some other kind of relationships, which a single tree-based decision tree can pick up. Also, correlation matrix fails badly in case of categories. So here, Bpscore comes to the rescue. It's a brilliant concept which trains one single decision tree to plot the importances of each of those category versus category interactions. Sorry, feature versus feature interactions. It also picks up the linear connections, as well as if it has a tree-based connections as well. So from here you can, you know, use it as a first line of defense for feature engineering and see if the features you generated are pairing up nicely with your target variables or not. If it's not, it's giving absolutely no result. Also, then I would recommend not to remove it completely, because there is one thing for single feature interaction, and there's other thing called feature on feature interaction. Like a month on alone cannot define target well, maybe, but a month combined with festivities column may very well define target. Again, festivities alone cannot define target. So you have to take into account the feature on feature interactions too, and that won't be showing in any of these matrices. So remember one thing: if you are not seeing any high score explaining your target by the features you engineered, don't get disheartened, because it may be picking up some interaction with other features and explaining target very well. One thing I did here was that I showed you guys how I, manually mapped all those item categories into new features and changed the whole item category into groups. And you can see in the PPS score, it's defining one thing that full screen. The brand. Where's the brand? Yeah. The product brand actually. And the class. So here is the class. Hang on, I just the class. So as you can see that this was my product brand. Now, how to read PPS score is on the left hand side, whatever is there, the horizontal bar is defining those. Like here, 0.42 is product brand is capable of explaining class by 0.42, not the other way around. But for collinear matrix, I believe this order is not valid. You can read it either way. Now, here, as you can see, the product brand is defining the class by 0.42. But if you see the product brand, how is class defining the product brand? Yeah, here's the product brand. And if you can see the class here, yeah, it's the end column. Here, this is the product brand, and the end column was my class, which I engineered. It's defining it pretty well at 0.78. Now, what this means is, as I showed in the beginning, product brand had huge number of unique categories. Now, I took care of one item category, which was also huge, and I grouped them, but I didn't as such take care of product brand till now. But I did make one feature class, which is explaining product brands pretty well. And now I have to think if I want to keep product brand in my data set. What I did was I removed product brand here because I want to avoid curse of dimensionality. It's a very bad thing. If I were to one hot encode thousands of categories, I'll be having thousands of categories. Then I have to, it will be a task in feature selection alone to use them in a proper manner. So I can go ahead and remove product brand from this analysis because I have managed to create a feature which is explaining product brand pretty well. And that is my class, which I explained before. So this is how you can take care of dimensionality. It's one way. There is another way to take care of dimensionality. Is if by chance you do not engineer such features, you can just go ahead and label encode them. Because if you are using a tree-based algorithm, and the tree, how the tree works is that it makes multiple splits on a particular column, right? So the splits will still make sense when you are label encoding the categories. But I've also seen that keeping the label encoded columns along with the one-hot encoded columns is better way, because sometimes it picks up some one-hot encoded column as important as well might be. So that is another way to avoid cursive dimensionality, label encoding instead of one-hot encoding. Now this is my data set, the final data set which I will be working on. It's product brand. So I'll be removing product brand below. As you can see, my item categories is pretty neat right now. It doesn't constitute of so many disintegrated information, and the rest of the columns are there. Brand keys which I use to map it, I'll be dropping it as bonus. And this was my target customer, which I engineered in the beginning. So now moving ahead, this is the simple split you have to do every time you start to validate your model. You have to uh, take only those columns which you think are necessary and put it into X, the target variables into Y. And I am dummy encoding the X features because there's still few categorical features like uh, clothing, festive. I did take care of item categories, but ultimately I changed it into aggregated categories only, so I have to take care of them now. So I'm not encoding them. And there is another thing called Cad Boost Features. As you can see, there are a whole lot of categorical features in this problem. Now, I've seen that Cad Boost works really well when you're dealing with categorical features. Uh, it gives you good results. So for categorical features for Cad Boost, you can take the int data types and object data types and put them for a categorical separate DF training for cat, which you will use later to validate for Cad Boost. Now moving on to the k-fold strategy. Uh, an ideal k-fold is one that makes your validation set as much as possible, close to possible as your test set. This is the in real world. This is what should happen. You should always validate your results on a matching as much matching set as possible to a test set. Then only you will be standing good in good positions in private leaderboard. Now these are the strategies that you follow if you are using classification problems. There is a stratified k-fold, I believe. You guys might be knowing it as well. For people starting out, this what it does is that it breaks the train set into it breaks the validation set into the exact ratio of classes which are there in the train set. So for example, if my majority class is 60% in train and 40% in 40% in minority, then my each validation set will also have the same ratio. And this is very helpful if my test set also represents my train set very closely. uh, I will be getting as close to it as possible in my validation set. That is the whole idea. For time series, you have to respect the temporal dependencies, because you can't train on a future data to predict your past data. This is not just possible unless you are using time machines. So there's a thing called time series split also in sklearn, and there are a lot of other k-fold validations which you can use for addressing these kind of problems, but never use a normal k-fold strategy for your time series problems, because then you will be just predicting past data based on future data. Now, this is where I'm plotting the distribution of the target price. Uh, as you can see, this is a highly right-skewed model. It's being said that for tree-based models, whenever you use tree-based models, you don't have to scale features, and it's true. But I've also seen that if a extreme skewness is present in the target itself, the tree-based models sometimes, tend to predict in a biased manner. Say, for example, if this has a 12 lakhs this the 12 lakh extends to 12 lakh. So all my predictions in test set, if the data in test set, for example, doesn't extend till that range, will have a bias towards the higher side. The problem rears in really badly when you have a left skewed, say for example, other than on the left side of zero, and your model will be predicting negative values instead for, say example, selling prices, which is not possible in real life. So if you forget this to normalize your target, if and only if there is a high skewness present, uh, check once what you're predicting, the results. If there are zeros in your minimum point, it's perfectly okay. But if negatives are coming in, you might consider normalizing your target or float them to zeros, the negative values. So this is what till now the normalization of target is. So having a recap of what we have discussed till now, the problem statement we discussed. In data exploration phase, I showed you how we can see if there are missing values present and all those stuffs. And for data pre-processing, how to deal with those missing values, outlier treatments, maybe anomalies which are present in the data. Feature elimination comes into play when you have a huge number of features explaining the data, and you might consider automated feature engineering to later on to, I'll be showing all this to handle them. So you might consider feature elimination technique then. Null hypothesis building is your all the initial ideas you had about the data set after seeing them, and you think the information that are not present in the data set, but you want them right there because you think that those will explain the target in a better manner. Feature engineering is acting on your null hypothesis to actually implement those ideas into action. And finally, setting up the validation strategy, using on which kind of validation strategy will suit your problem so that your validation sets will as closely resemble your test set as possible. So here is my k-fold validation strategy. Now, another thing you have to be actually wary of is maintaining a stock codes, because as competition rises, you will be using the same codes again and again, and it's very bad habit to write them from the very beginning. Make no mistakes, if you're doing this for learning Python like I started to do it, you'll still be learning a lot. You'll learn to code, it doesn't matter, but you will be saving your time to write the same thing again and again. So I pretty much use this validation strategy everywhere. Uh, I edit them when I do feature engineering, and like here I did target encoding, and I should have put the target encoding part of engineering inside the validation set. But again, this was one of my first hackathons, and I didn't know so much about the validation strategy, so I didn't do it. But I recommend you always, if you targeted code, you always put them in your validation strategies to see if they are really working or not, and if you are overfitting or not. So this is what I did over the evaluation metrics that the MachineHack guys provided me with, RMSLE, and these are my scores in the beginning. Now, there is a view of OOF versus full fit in validation strategies. The reason people say, you'll hear a lot of people say that you will win this problem by how you set your validation strategy by. What I am using my validation folds here, K folds here, is only to validate my model and nothing else. I see what is working, what is not. If a particular feature is working, I keep it. If a particular feature is not working, I do not keep it. And later on, I use them to hypertune my model. But when I'm submitting my submissions, I still use a normal full fit. That is, I fit my model in the full data. Now, you can also use out of fold predictions to make your submissions. Like inside a validation strategy, if you have a test set if you are training on a particular fold of a train set, say X train here and Y train here, you can train on it and then predict on the remaining on the whole test set, and then try saving it under a variable and keep on saving those things and later average them out to get the OOF predictions, and you can submit them. How this helps in is in generalization of your model predictions. It's one way to generalize. There are many ways to generalize. This is one way, and it also helps if your data is huge and you do not have time to train on your whole data. You can break it into parts and train it, but I guess I don't know if breaking into 5-6 parts may cost greater time than fitting it once. I generally do not use OOF that much till now. Whatever I do, I generally do it in full fit because I have this nagging feeling that I'll be losing out on information if I don't use the full data. I may be wrong. So now comes selecting your features. Now this is a code I wrote after considering how we work with feature engineer k-fold validation sets. Whenever we uh, do any validation folds and then we select k-best features or stuff like that, we do not uh, consider all the folds for selecting the most important feature. If you think about it, each of your fold, say 1, 2, 3, 4, 5, your you did your validation, you got your scores, and now if you plot the k most important features, you're plotting basically the features from the last fold. Now, for tree-based model, the order in which the k splits are made are not always the same. There's a degree of randomization, and the chronological order of every tree split may not be same. So a feature which comes very important in your first fold may not be that important when a separate part of your train set is being used to train the model. A new feature may come as the most important feature. So there is a need to average out all these important feature scores and get the average picture of what this k-fold strategy gives me. So this is why I wrote this line. But what this code base does is it calculates the feature importances and it stores it in this L variable. And later I average it out all from all the folds to look at my feature importances. Now, when I'm plotting this thing, this is not only plotting the feature importances from the last k fold, but it is also plotting the feature importances from all the k folds averaged out. And this is where I believe you will be gaining a lot if you take into consideration all the k folds. So moving on, the next part, uh, what we did here was that we will be using all the models that we decided in the beginning, and now I use separate kind of models. The reason behind this is that you have to ensemble in the end, and ensembling works best when you use different models with different features and you have least collinearities between them. So first I used Cad Boost model to train my model, train my k-folds, and then I used gradient boosting, and finally I used extreme gradient boosting, and this shouldn't have been done. I should have used light GBM or something like that, but this was beginning of my data science journey, so I used pretty much similar models for the last two sets. And how I do feature selection is I look at my averaged out sets. I leave the last feature out and then again validate it in the case fold and look again and see if it improves the scores a bit. If it's not if it is not improving, I remove that feature and remove the second last feature out maybe, and like that. It's a bit of a trial and error really like now, unless or until someone comes up with a better library. Uh, this is my selected features right here that I selected for each of those models, and I'm using those features only for the specific models, and uh, you know selecting them from the test set. And finally, I'll be hyper tuning these models based on these features. I always do hyper tuning after feature selection, because one, if you do hyper tuning before feature selection and then again you have to do hyper tuning after feature selection, it's a lot of work. So it's very similar if you follow either of the strategies. I did full grid search here because the data was small. You can do random CV search also if your data is huge, or follow completely different methods like the Bayesian methods. They are fast and gives pretty much accurate scores. These are my hypertuned parameters which I used. Nothing to explain here. These are just parameters. And finally, I'm fitting the models on the whole set, as I said before, and storing the solutions in each of these variables. Now coming to blending. It's always a good idea if you are approaching a hackathon alone, you need to start thinking how you can blend from the beginning. If you think that I'll select a base set of features, say 10 features, and I'll use them in every model, and then change the feature parameters maybe a bit, and then blend, it still works. But it almost never works if you just use random models with the same features and don't even change the parameters. There has to be some form of randomization in your blending mechanism for it to work, because collinearity, correlation among the model is a huge thing. You may actually see your voting regressors and stacking regressor scores go down if there's a huge correlation between the models you're using in your blending. Uh, if you're going, if you're not using any models like voting regressor or stacking regressor, you may go like this. Simply multiply your solutions with a particular weight, and then you can change these according to the score you are getting on the leaderboard. If your leaderboard score is going up, you may want to keep it. If your leaderboard score is going down, you can change it and keep on changing it till it works. This is called leaderboard probing, basically. So there's another way to blend these things. You simply plot in Excel all your features, all your no, predicted prices, column by column, and simply plot a correlation matrix to see which model predictions are the least correlated, and you go by them for blending. So this is pretty much it as far as the solution to this problem was concerned. Now I will be sharing some of the tricks and hacks I used to counter the all those problems of scoring, increasing the score in a leaderboard. So coming on to the tricks and strategies, first is automated feature engineering. This works well if mostly my features are numeric in nature, and you have a bit of lesser dimensionality to begin with. Say for example, if I already have 75 to 76 features in a columns, you may not want to consider this mode and go for a rather manual mode, because it will take a whole lot of resources on your end. The second con I thought was that the explainability of this feature, automated feature engineering to your clients if you're doing it in your real life. What I thought was that if there's a thing called max depth for this function, if you increase it to 3, if you keep it at 2, what it does is it basically takes all two combinations of 2 columns and performs the functions that you have mentioned. But if you keep it at 3, it will similarly take all combination of 3 columns. Now this may not be a good idea, because after a certain level you yourself won't understand what those features mean, and that may be still increasing your score in hackathons, but you won't be able to explain the meaning of those variables. So that is one thing you have to keep in mind. Second comes into play role of unsupervised learning in creating clusters. So this is a pretty simple idea I used sometimes, that you run a basic k-means algorithm on your data set and start predicting, first decide on how many clusters to narrow down on, and then you run a cluster module to predict all the possible clusters in your data set and keep them as a feature. Like here I did a tree cluster was one of my features. Now how this helps is that if there is a pattern to be recognized in your numerical variables, this cluster module will recognize it, and it will help explaining your target features as well. This clustering should always be done by first identifying the ideal number of clusters, because if you use too many, maybe the curse of dimensionality comes into play again, and if you use too less, it may not be explaining or catching all the variations. Usage of pipelines. This is actually the mistakes I did in the beginning. So what I used to do was I used to select features, all features of different models, different features, and then put them in a single voting regressor like thing, or stacking regressor, and train them or fit them in the whole on the whole train set. Now what is happening here is that you're selecting different kind of features for different models, but you're not respecting those model feature combinations. You're training them on the whole train set. This is where pipeline comes into play. You can first mention all the features you have selected for each different models, and then use pipelines to ensure that all those separate models get only those features to train upon. And this is how pipeline helps you uh, respect those combinations as well. Now, voting regressor classifier, weights and brute force. You have all used voting regressor in hackathons. Uh, Voting regressor, what many of you don't know actually, is that it does comes up with a attribute of weights. You can actually set weights of how much you want to give to each of the regressors. Now, if you are using a voting regressor, always try to use 3 models instead of 2. And for the weights, they not tend to normalize these weights, and thus you are basically blending. If you think about it, you're blending your prediction results. So another alternative to leaderboard probing is to blend these weights in a brute force kind of manner, which this code block explains. What I've done is I've run 2 for loops for 2 combinations of weights that my model had, and simply trained them on a cross validation of 5. And ultimately I'll be printing those values in a sorted manner to see which ideal combination of my both models works best on my current problem. So this is one way to do it, instead of if you are tired of leaderboard probing. But I'd still suggest that blending in the leaderboard probing works well better. But if you do not have time or just feeling lazy, you can do it. Now the concept of pseudo labeling. This is a very interesting thing that worked for me once. Uh, what this means is training back your model on your predicted values, and again fitting the model. How this works, the literature that I have read so far says that it helps the model better build the decision boundaries than already present if your train set is relatively small and your test set is pretty huge compared to a train set. So for this, I was searching a way to implement it, and I found this article by Shubham Jain. He wrote this class of pseudo labeler. This is optimized for regression problems only, and this is a beautiful class. You can use it for fitting on any model. this class, you have to simply mention the pseudo labeler and put in the variables inside them, and it will just go ahead and train all your models, predict the results, take the results back, fit again, and give you the final predictions. I refitted this class with to account for ensembling part, because he didn't write it keeping ensembling in mind, I believe. So I made it suitable for ensembling also. So if you use this in ensembling methods, it will still work. Next is a reducing class for reducing memory usage. This is pretty much very basic. Anytime you deal with large data sets, you have to use this, because or else there will be too much hogging up your RAM in your system memory. Lastly, I'll be explaining duplicates handling. Uh, Now, this is a very important thing that I found out in my tries with hackathons, that there may be cases when there are rows in test set which are exactly there in the train set. What this also means is the test set values, some of the test set values you already know, but you are still training a model to predict them. Now, the way decision trees work, this may be fine for a classification model, but for a regression model, as the last end node of every decision tree averages out the value to give us the prediction as we know, averaging out known value may not always hit the right prediction. Why should we average out if you already know it? So what I did here was, I follow it sometimes if I find duplicates. I tend to manually impute them in the test set and work on the rest of the test set without the duplicate. So I wrote this function here, you can see it. This is a pre-duplicate handling. This function takes in your target set, the key of your columns that you want to use to find the duplicates, and return the test set without the duplicates. Now this function always has to be used with a post-processing module, where mostly the test final set, where you'll be getting the test final set and you'll be predicting on the test final set. You have to use the test set that was in the very beginning and impute only those values that were not handled by the duplicates. This is what this block of code does basically. So that's pretty much it. Lastly, tree-based models work better with dense features than OHEs. I discussed this already. And yeah, so ending notes, each and every single feature you engineer or feature you eliminate, each and every missing value you delete can have a potential to increase your scores. You have to keep on trying. You have to have a good careful strategy, and always try the simpler things first. And you may never know, can be a data leak also, like some important information lying in the ID columns maybe. You explore all the paths available to you in the stipulated time, and keep the ensembles for the end so that you may get a good score. So yeah, that's pretty much it what I had to explain. Hello, Anurag, are you there?
Yes. So
Okay.
I would like to thank you, Devrup. It was a great session.
Yeah.
So Q&As will be now handled. So I have filled you some of the questions. Can you see them?
Where will I?
So on the right side on the
I
questions.
yeah.
Yes. So few of them are very much around the problem statement which was discussed, ranging from the correlation, or what was the cutoff of the correlation, and things around multi-collinearity. So if you could just answer a few of them.
So the first question I can see is, can you explain on how do we consider these null hypotheses? Okay, so
Yes, that's right.
so null hypothesis, as I said, the feature engineering. Well, the moment you see the data frame, you have to build on your null hypothesis. It comes from an idea that you want some information which you think will be relevant to your problem statement, but is not being defined by the features that are already present in your data frame. So keeping this in mind, you build questions, you build unlimited questions, as many questions as you can, and try to implement them in your feature engineering part. Because feature selection won't be a problem, but you may miss out on few important features if you do not think enough in the null hypothesis part. So the next question, I guess, is that is there any way to automate the target encoding did manually? I understand that there are a huge number of unique data, but some sort of automation is to reduce the time it is spent to the presentation. Target encode. I did not do the target encoding part manually. I did the aggregation of categorical features manually. See, there are models, the SOTA models, which for NLP you can use to extract topics from a line of a string, I believe, and you can use them. But again, relying on a model to extract information that you will do it better, I thought why not do it manually then. But yeah, there are SOTA models which you can use to extract the topics. So the next question is, if you are using tree-based algorithms, when is it necessary to use outlier treatment? For tree-based, the outlier treatment doesn't actually depend on the kind of model we are using. It depends more on the problem statement and what your client requires, maybe. Because if I see that my test set is considerably different from a train set, that's when my outlier treatment thing comes into play. I have to start considering this angle. But if I do not see that much difference in distribution of each features in the test and train set, I will be, avoiding outlier treatment as much as I can, because one of our teachers used to say that actually never do outlier treatment. In most cases, you'll be losing out on information. So if you have reason to believe that the outlier treatment is absolutely needed, that the extreme values are wrong and not an extreme case, it are basically wrongly imputed, only then go for outlier. So the next question is, what is the cutoff for this new correlation matrix, and what cutoff say that a field is defining of a field well? Yeah, Bpscore. They have kept the cutoff at 0.65, I believe. I have to read the documentations again, but they have explained this very well. How they got at the cutoff was they trained a naive model first, and they said that the score that a naive model will be getting, explaining each individual feature single-handedly, will be my cutoff, will be my baseline. And above this, if your features can explain the target better, then the difference in scores will be shown in the PPS score. This is what they are doing. So you can use PPS score, and it's a very good, correlation matrix to use. It's better than correlation matrix, actually, I guess. So I'm a beginner, but have good understanding of programming in Java. I'm doing PGDDS. I have also deep understanding of different subjects like economics, how to consider okay. So yeah, if you want to keep in data science, economics is a very good place to start, I believe, and statistics. And I may not be qualified to answer this question right now because I'm still looking into my first profession. Shall be joining. So I believe you have to consult someone right, better mentor for this. As far as resources are concerned, I will be providing you with a few of the links to the GitHubs and Medium articles that I found helpful, and they will be very good if you consult them. Yeah. So I guess that's it, Anurag.
Yes, I guess that's it from the Q&A side. So I believe we are not getting any other question. Okay, yeah, we just got one more. Is the ranking only parameter to look at the hackathon, or the approach is also reviewed? Mhm.
I believe Anurag is more qualified to answer this. Anurag, you can shed some light on this. Do you people
Yeah,
consider the approach?
so I'm not able to get this. It's by Pancham. So Pancham, is it possible to put more descriptive question? So what sort of ranking
I believe
you are talking about?
she's saying that the score he gets on the leaderboard, is it the sole criteria, or you guys look at the approach also?
Oh, okay, yeah, yes.
Yeah.
So no, primarily we are not dealing with the approach. We are just looking at the leaderboard. So leaderboard, however, let's say it's a sort of automated way of kind of ranking people based on the metric. But let's say to prevent sort of overfitting, or let's say learning and identity function, which is like a copy paste stuff of the data, we have kept a private set, which is let's say 30% of the test set, which is not evaluated when a person is submitting during the hackathon. During the course of hackathon, that data set is not used. And when the when the hackathon gets closed, then we sort of evaluate the private set. Is there a link to train and test data set? I think, yeah, the data set is for one of our hackathons. So we have shared the link for the notebook in the chat. I'll just ping it again. So for which hackathon, Devrup, this was?
This was the e-commerce price prediction hackathon.
E-commerce. All right, I'll just ping the link here. All right, and meanwhile, I'll also like to announce one of our upcoming hackathons, which is predicting the GitHub issues. It's a sponsored hackathon, so there are a lot of prizes to be won, so you can stand a chance to win some of prizes. So this is a very interesting hackathon where you have to predict the it's kind of evaluated based on accuracy, and you have to kind of foresee the bugs, features, and questions on GitHub issues. So kindly requesting all to look into it. I'm just pinging the link in the chat to all the audience.
I'd like to add that the thing that happened with me was that the hackathon was pretty interesting and I didn't know where to start with the GitHub hackathon. But later he explained to me that there's a full-fledged tutorial and documentation, and it's actually pretty simple, the UI. So if you find the problem interesting, you
Right.
can go ahead and participate. It's no issue.
Yeah, link to kind of, let's say, quickly understand the platform. Yeah, so this YouTube link is also available on the platform homepage. You can see under the overview tab. So this kind of was available to us from Embold itself. This is also available publicly on YouTube. So everybody can just have a quick look. It's a 2-minute short video describing how to use Embold's platform, kind of a go-to sort of stuff. So any other questions? I think, let me check. Okay, so a lot of people are thinking about the Jupyter notebook.
Yeah, I've
Yeah,
shared
and the session. Right. So yes, so the link is shared in the chat. Also, the link will be mailed to all the participants with the recorded session. So both the links will be shared. It will be an open URL. It's a public link. People can access both the notebooks and the recorded sessions for this webinar. So if anybody has any questions, I see there are still some questions coming in. Just a moment. Yeah, I think therefore we can close it now. There are no more relevant questions.
Okay.
Yeah, so it was a great session. I'd like to thank you for joining hands and kind of contributing to the community. Looking forward to see more in the future. Yes.
Yeah, thank you, Anurag. Thank you so much. And I'd like to thank Analytics India Magazine for starting this webinar series. I believe we'll be seeing more and more hackathon experts here sharing their approaches. And sharing is the best way to learn in data science, considering the evolving field it is. So yeah, it's a great initiative.
Absolutely. Yep. Thanks a lot, Devru. Thanks again.
Yeah.
Yep. So I'm closing the session. Yep. Thanks.